Hello and welcome to the Forth Valley and West Lothian RIC supported study resource. This presentation will take you through how to solve double angle trig equations at higher level. Throughout the presentation there will be three icons that will be on the screen. There will be a little ear which is a listening page, then there will be one where you've got to pause to complete a task that will be set, and then the one with the tick will be the one where you can go ahead and correct your work. The learning intentions throughout will be to learn how to solve trig equations involving double angles. What we'll be looking for in terms of success criteria is being able to identify the correct expansion to solve a double angle trig equation, for then being able to work through the methods of solution for each equation, and then know which solutions are appropriate for each question depending on the range that's supplied. Okay, we'll explain all of that as we go through them. First of all, what exactly is a double angle trig equation? So exactly what do we mean when we talk about double angle trig equations? Okay, well these are equations of the type cos 2x plus sin x minus 4 is equal to 0, or sin 2x plus cos x equals 0. As long as one angle in the question is double the other angle in the question, you have a double angle trig equation. Okay, so 2x compared to x is obviously double. Similarly here, 2x and x. Doesn't matter whether we've got sines, coses, sines, doesn't matter, cos. As long as one angle is double the other angle, we have a double angle trig equation. So that's what we're looking out for when we're doing these questions. Now, before we can actually do these questions, there's a wee bit of assumed knowledge that you've actually learned earlier on, either at National 5 level or at higher level. And what we need to be pretty good at to solve these is knowing and using the cast diagram to solve trig equations. Now, this is a skill from National 5, where we have the all sine, tan, cos quadrants, and the related acute angle x and how that develops into each of the other quadrants as 180 minus, 180 plus and 360 minus. Also, we need to know how to factorise. It's quite a lot of factorising. We need to know the exact values. We need to know the relationship between degrees and the radian measure. And we need to know the expansions for sin 2x and cos 2x. These formulas are given at the front of the exam paper, of course. Now, I'm going to take you through a quick reminder of the assumed knowledge, just so that you're all clear exactly what I mean by those 5 items on the last page. Okay, so for example 1, let's solve sin x equals 0.4, and we're going to do that for x between 0 and 360 degrees. Okay, so the question is sin x equals 0.4. Once we get to sin x, cos x, or tan x equals, the next thing we're thinking about is the cast diagram. Okay, from this example, it's a sine question and it's a positive number. So that means we're going to tick the sign in the A quadrants. The answer in the sine quadrant is 180 minus. How do I get an answer in the A quadrant? Then that's reasonably straightforward. We get the calculator to do the work for us. Inverse sine 0.4, and the inverse sine 0.4 from the calculator comes out to be 24 degrees. So your first answer is 24 degrees, and your second answer is 180 minus the 24 degrees, which is 156 degrees. For the second example, let's do one slightly harder. Let's do solve 4 cos x plus 1 is equal to 0. Keep it the same range for x to be between 0 degrees and 360 degrees. Now before we get to the cast diagram this time we have a wee bit of work to do. Okay, because we need to turn the 4 cos x plus 1 equals 0 into 4 cos x equals negative 1 by moving the positive 1 over, and then moving the 4 over, we get cos x equals negative 1/4. At this stage we can go to our cast diagram, all sine, tan, cos, remember the order. Now we're looking here this time at a cos question and it's a negative value. So the cos negative values happens in the sine quadrant and the tan quadrant. Okay, the answer in the sine quadrant we've just seen is 180 minus. The answer in the tan quadrant is 180 plus. Okay, get the answer in the A box, the all box, where they're all positive. How do we do that? We do the inverse cos and we temporarily ignore the negative sign. And the inverse cos of 1 divided by 4 on our calculator gives us an answer of 76 degrees. Okay, I've written it in the A box, so it's not part of our answers because it's not got a tick there. Our answers come by doing 180 minus the 76, which is 104, and 180 plus the 76, which is 256. Okay, so that should be a quick reminder of how to solve these equations from National 5. If we remember the two types of factorising from National 5, i.e. common factor. Now if you remember, common factors we did in National 5 might be along the lines of xy plus 2x. Okay, so is there anything that appears in each part of this expression? And there's an x here and an x here, so that would go as a common factor. It would leave you with a y plus a 2. Okay, now when it comes to higher maths, then it gets slightly more complicated than that, but the principle is the same. So you might get things like sin x cos x plus 4 cos x. So again, is there anything on the left that's the same as the right here? And I can see a cos x and a cos x. So that tends to indicate to me that I'm going to put the cos x on the outside, and then I'm going to be left on the inside with a sin x add 4. Okay, so we're looking for common factors. And then the other type that we're familiar with is trinomial factorising. Okay, now if you can remember what that is, brilliant. If not, then it's a sort of question along the lines of x squared plus 3x plus 2, which factorises into x times x for x squared at the start, 1 times 2 for the 2 at the end, and they're all positive, so plus 1 plus 2. Again, for this particular part of the course, but we're not going to just use x's, we're going to use things like sine squared x plus 3 sine x plus 2, and we're going to factorise that. So all I've done is change the x's to sine x's. So in my brackets I would have sine x plus 1 and sine x plus 2. Okay, so it's your factorising that you did in National 5, just moved up to a step for higher. So if you remember, the exact values come from two triangles. The first one is an isosceles triangle, which has angles of 45 degrees, sides of 1, 1 and root 2. The second one has angles of 30 degrees and 60 degrees and sides of 2, 1 and root 3. Okay, now they are right angle triangles. So we have from these exact value. Sine 45 is equal to, well, there's the sine, there's the opposite side, root 2 is the hypotenuse, 1 over root 2. Cos 45, also 1 over root 2. And tan 45, opposite over hypotenuse, 1. For the 30-60 triangle, then sine 30, opposite over hypotenuse, 1 over 2. Cos 30, adjacent over hypotenuse, the adjacent one is here, one next to it, so that is root 3 over 2. And then tan 30, opposite over adjacent, 1 over root 3. And then the last one would be the 60 degrees, so sine 60. This time this is the opposite side, so it's root 3 over 2. Cos 60 is a half, and tan 60 equals root 3. Okay, so you need these exact values. At this point, it would be worthwhile taking a note of that screen of those exact values because we're going to use these in the questions later on. Okay, so we know from previous work that 180 degrees is equal to pi radians. Halving that to get 90 degrees is obviously half of pi radians, so pi over 2 radians. Now 30 degrees, that's a good one to remember. 30 degrees is pi over 6 radians. Okay, why is that a good one to remember? Because if I need 60 degrees, then it's just two lots of that, 2 pi over 6, which can cancel down to pi over 3 radians. If I go a wee bit more complicated, I'm looking for 210 degrees. Well, how do I get 210 from 30? By multiplying it by 7, so that'll be 7 pi over 6 radians. So a good one to remember is the 30 degrees. Another one to try and remember would be pi over 4 radians is equal to 45 degrees. So if I was asked for something like 3 pi over 4 radians, then that would be 3 lots of pi upon 4, 3 lots of 145, which would be 135 degrees. Okay, so you need to be able to go from degrees to radians and radians back to degrees, as I've done with these examples. Now from your work on expansion formulas, and if you can't remember them, the good news is at the start of the exam paper we have some formulas which are going to come in handy for this section. Sine 2a can be expanded to 2 sine a cos a, and cos 2a can be expanded to cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. And I'll explain when we use which of these formulas in the questions as we go through this presentation. Okay, the sine one is good because there's only one expansion, but the cos one I'll explain which one we use and when. Okay, so in general, what we're going to be doing to be solving a trig equation is we're going to take some sort of horrendous looking equation, something along the lines of 3 cos 2x minus 5 sine x plus 7 equals 0. So something that involves double angles and sines and coses, and we're going to manipulate that, do some work on that particular equation, and we're going to end up with a nice wee simple sine x equals or cos x equals. So this part in here, this middle part, right, that's the main work we're going to be doing for higher. Once we reach sine x equals and cos x equals, we're back to Nat 5 work. We know how to solve these things. We're either going to use the cast diagram or we're going to use the graphs of these functions. So the sine graph, remember, looks like that, and the cos graph looks like that. Okay, so starting with something horrible up here that involves double angles, sines, coses and much like, do some higher manipulation on that, arrive at sine x, cos x equals, solve using the cast diagram or the graphs. So the big question is, how do I go from some horrible looking equation up here? What's the process that I go through to end up with a nice wee cute set of equations here? Okay, and there's basically 3 steps that we go through. Now the first step is to expand. The second step is to factorise. And the third step is to solve equal to 0. So if you can remember those 3 steps, okay, do your expansion, do your factorising, solve your factors equal to 0 as your third step, okay, then you'll be able to do double angle equations. Okay, expand, factorise and solve. That's the method that we're going to be using when we do these questions in a minute. I'm now going to take you on a walk through to 6 different questions about solving these equations. Okay, remember from the previous slide, what we need to be thinking about is expanding, factorising, solving. Okay, that's the 3 steps that we're basically going to go through. So here is example number 1. So solve the equation sine 2x plus cos x is equal to 0, and let's do that for x to be between or equal to 0 and 360 degrees. So the first thing we do is we're expanding. So sine 2x, we know the expansion for that is 2 sine x cos x. Cos x, can't really do an awful lot with that, is equal to 0. Now equal 0 is quite important all the way through these examples. Factorising. How do I factorise this? Well, looking at the expression I see there, I can see a cos x here and I can see a cos x there. So I'm going to take that to the outside as a common factor, and that's going to leave me inside a 2 sine x plus a 1 is equal to 0. Now we solve each factor equal to 0. So the first factor is cos x, so I'm going to solve cos x equals 0, and then I'm going to solve the second factor, which is in a bracket, 2 sine x plus 1 equals 0. So the first factor equaling 0, this is a special one, so we need to go to the graph for cos x and identify the places where it's 0, and we have these 2 points here, and they happen when x is 90 degrees or 270 degrees. For the second factor, I'm going to rewrite it slightly as 2 sine x equals negative 1, taking the plus 1 over, dividing by the 2 gives me sine x equals negative a half. Going to my cast diagram, what am I looking for? I'm looking for a sine value which is negative. So I'm going to tick the T in the C boxes. That's where my answer is going to lie. Okay, we're fortunate this is an exact value. So when does sine equal a half? We know that that is 30 degrees. Again, note I'm writing it up in the A box because it isn't part of my answers, because it's the ticks for the answers. And the first tick is 180, add 30, which is 210. Second tick is at 360 minus 30, which is 330 degrees. And there, if I put it all together, I can have my solution as, and it's nice to write it out in order for the person who's checking your work, 90 degrees, I haven't said that, I didn't put it in order, right, 90 degrees, 210 degrees, 270 degrees, and 330 degrees. And that's your double angle equation solved. Here is your expansion line, your factorising line, and the bit with all the work in it there is your solving the little equations. I'm now going to take you on a walk For the second example, I'm still going to stick with my sine 2x. This time I'm going to solve sine 2x minus 3 sine x is equal to 0, but this time I'm going to change the x has to be between 0 and 2 pi. Okay, so in other words, we're working it out in radians. Right, remember, expand, factorise, solve. So again, the expansion for sine 2x is 2 sine x cos x. Can't do much with the 3 sine x, so I'm just going to leave that as it is, equal to 0. Factorise, no number will divide exactly into 2 and 3. However, I do see a sine x in both parts, so I can take sine x out as a factor, leaving me inside 2 cos x at the start and minus 3 at the end of my bracket. Solving each of these factors equal to 0 gives me sin x equals 0 or 2 cos x minus 3 equals 0. Again, sin x equals 0, that's one of these ones that we get from the graph. So there's your sine graph. When is the sine graph 0? Here, here, and here. Now your brain's probably going 0 degrees, which is the same as 0 radians, 180 degrees, which is the same as pi, and 360 degrees, which is the same as 2 pi. That's fine. Second equation to solve, 2 cos x equals 3, and then cos x equals 3 over 2. Now, cos x, when does that equal 3 over 2? If you try on your calculator, you're going to get a math error. Okay, thinking of the cos graph, it goes between 1 and minus 1. We're asking when does it equal 3 over 2, when does it equal 1.5? Well, that's this point up here, so when does the graph ever reach up there? Well, it never does, because it only goes between the 1 and the negative 1. So this is impossible. And it's important that if you do get any solutions that are impossible, that you actually indicate that they are impossible. Just don't miss them out. Okay, so your solution for this question, it only comes from one of the brackets, is that x is equal to 0 radians, pi radians, or 2 pi radians. Okay, we'll mix it up a little bit for the third example. So let's go for this time cos 2x plus cos x equals 0, and we'll do this one first of all for x to be between 0 and 360 degrees. Okay, the fact it's a cos 2x question doesn't make any difference. We're still going through the usual procedure of expand, factorise and solve. Okay, problem we have here though is when we look at the cos 2x, we have three expansions for that, because we can either put in there cos squared x minus sine squared x, 2 cos squared x minus 1, or 1 minus 2 sine squared x. Okay, so we have a choice. With the sine ones we didn't have the choice. The cos ones we need to make a decision. Which one of these three formulas are we using? Okay, now the whole point is we're trying to make things a wee bit easier for factorising. If I put cos 2x and take that away and introduce cos squares and sine squares, I think I'm making it a wee bit harder, because I've got, first of all, squares in it, and I've got coses and sines, and that's not going to lead to factorising very easily. The second one, can I use 2 cos squared x minus 1? That might be possible, because I've got cos squared x's and I've got coses in the question, so that one's looking favourite just now. Okay, that one's looking good. And what about 1 minus 2 sine squared x? Well, again, it's pretty much the same as the first reason. If I start introducing sine squareds and I've got coses in the question, that's not going to factorise very easy. It's going to like try and factorise things with x squareds and y in them. Okay, so I'm going to stick to the second method. So let me remove the first one, because we're not going to be using that. And let me remove the second one, sorry, the last one, because we're not going to be using that as well. Okay, so I've picked the correct expansion, 2 cos squared x minus 1, based on the fact it's got coses in it, and there's coses in the question here, plus cos x is equal to 0. Now, before I do any factorising, it would be a good idea if I could get it into like the quadratic form. So the squared term, then the linear term, and then the constant term at the end. So 2 cos squared x plus cos x minus 1, written like that. Now we need to factorise this, and we're factorising it into a pair of brackets, equals 0. Now some of you might be a wee bit scared when you look at that and think, how on earth am I going to factorise that? Okay, well if I tell you factorising that is just the same as factorising 2x squared plus x minus 1. Okay, something that we've been good at factorising in National 5. 2x times x for 2x squared, 1 times 1 for 1 at the end, and then 2 times positive 1 to give us 2, take away 1 to get the 1 in the middle. So factorising this gives these two brackets. If I apply the same method here, then that's going to give me, oops, I'll get rid of that. That's going to give me 2 cos x minus 1 and cos x plus 1 as the two factors in the brackets. Okay, so you'll have noticed that when it was a sine 2x question, the previous ones, it was a common factor. When it's a cos 2x, it tends to be a trinomial to factorise. Not always, but most cases it's a trinomial to factorise. Okay, so we set the first factor equal to 0. So when does 2 cos x minus 1 equal 0? And then we set the second factor equal to 0. When does cos x plus 1 equal 0? Okay, rearranging this first little equation, we get cos x equals, take the negative 1 over, take the 2 over, we get cos x equals 1/2. Just let me slide this up a wee bit so that we can get a bit more space. Right, when does cos equal a half? Looking at our all sine tan cos diagram or cast, cos being a positive number would mean we're ticking the A quadrant and the C quadrant. When is cos equal to a half? Again, luckily for us, it's an exact value. So that happens at 60. And then in the C quadrant, 360 minus that, 300. Going back to the second one, don't forget you've always got two of these to solve. Moving the positive 1 over gives us cos x is negative 1. From the diagram for cos, where does it equal negative 1? Down here, when x is 180 degrees, only the one place. We can then write down what the solution is, putting them in order. The solution is x equals 60 degrees, 180 degrees, 300 degrees. Okay, so just give me a wee second. I'm going to go through this one again with you because it is a wee bit more involved than the sine one. So there was our initial expression at the top there, cos 2x plus cos x equals 0. We picked the correct expansion, 2 cos squared, factorised the trinomial, solved each of the factors to get the answer. Okay. So for example 4, I'm going to try cos 2x plus 3 sin x equals 2. And I'm going to solve this one for x to be between 0 and 2 pi. So in other words, we're doing it in radians again. Right, as soon as you see that radians, then your brain should start thinking exact values, not always, because remember you can switch your calculator to radians, right, and you can do these calculations with your calculator on radians instead of degrees. Okay, so cos 2x. So again, I've got my choice of expansions. What expansion do I want to use? Now, because in the question this time I've got a sin x, then I'm going to use the sine expansion, which is 1 minus 2 sine squared x. So I've picked my correct expansion, plus 3 sine x. I'm going to take this opportunity to bring the 2 over, because remember what I said earlier, we want to try and keep that right hand side 0. Right, it will help us when we come to doing the solving part. Rewriting this in like the quadratic form, I've got minus 2 sine squared x, I've got a positive 3 sine x, and then if I deal with the constants, I've got a 1 here, I've got a negative 2 here, and 1 take away 2 gives me negative 1 equals 0. Now I need to do some factorising. Two things are probably causing you issues here. The fact that we're factorising things with sine squareds and sines in them, but also this negative sign here at the front. One of the reasons that we made this 0 on the right hand side here is because as soon as we make that 0, that gives us license to change this to positive 2 sine squared x minus 3 sine x positive 1 is equal to 0. Right? Please note you can only do it because it equals 0. We can't just do that at any point we fancy at any time in the course. Just change signs willy-nilly. We can't do that. Right? We need to have it equal to 0 and then we can change the signs. Okay, so now we've changed the signs, we can think about factorising. 2 sine squared x comes from 2 sine x times sine x. 1 comes from 1 times 1. If there's a negative sign in the middle and a positive sign at the end, we know these two signs must be negative. Okay, you'll have your own way of factorising these trinomials. So once you've factorised it, then we've got the first bracket which says 2 sine x minus 1 is 0. Second bracket, sine x minus 1 is 0. So working with the first one, then that's going to give us sine x equals taking the negative 1 over, taking the 2 over, sine x equals a half. Again, give me a second, I'll just move this up a wee bit so I've got some space to write. Once we've moved it up, we will have, when does sine x equal a half? From our all sine tan cos diagram, sine being a positive value means we're ticking these two boxes here. Now your brain is probably going, when is sine a half? It's a positive value, it's 30 degrees, but remember the question says do it in radians. So we're working this out in radians. So your answer isn't 30 degrees, it's pi over 6. Second answer, your brain's probably thinking 150, but you're going to write down 5 lots of 30, 5 pi over 6. Okay. Sine x take away 1 is 0 for the second factor. That would mean sine x equals 1. That comes from your little graph for sine. When is sine equal to 1? This point here, which is when x is, and again your brain's probably going 90 degrees, but you're writing down pi over 2 radians. Okay, once you've got all of that, we can then write down what the solution to the question actually is. And the solution is in order pi over 6 radians, pi over 2 radians, and 5 pi over 6 radians. Okay, for example number 5, I'm going to step it up a wee bit. Okay, so this time I would like you to solve for me 2 sine 2x plus cos x is equal to 0. First thing we notice here is, oh, wait a minute, we've introduced a wee number in the front there. But that wee number in the front doesn't affect your expansion at all, right? It just means it's 2 times whatever your expansion is. And your expansion for sine 2x is 2 sine x cos x, and then plus your cos x equals 0. Okay, so the 2 just means double your expansion, which would be 4 sine x cos x. Now I know there's some of you out there who might just go straight from that line to this line here, 4 sine x cos x, that's fine. Okay, plus cos x is equal to 0. Okay, so we've done our expansion, we've done our tidying up. Next step is to factorise. So I've got a cos x here and I've got a cos x here. So I'm going to take cos x as a common factor. So cos x bracket 4 sine x plus 1 is equal to 0. First factor equal to 0. Second factor equal to 0. First factor being equal to 0 comes from the little diagram for cos. I think we've been here already with this one. Okay, that happens at the point on the x-axis here and here. So that is when x is equal to 90 degrees and 270. Sorry folks, I've just realised I didn't tell you I was doing this one, my mistake, between 0 and 360 degrees. So 90 and 270 degrees. The second example, we need to rearrange that formula to get sine x equals, now the 1 goes across as -1, the 4 goes across as divide 4, and on the cast diagram, it's a sign question, it's a negative value, so that means I'm going to be ticking the T and the C boxes for this particular example. Calculator for inverse sine a quarter tells me it's 14 degrees. So the answer you're going to be looking for is 180 add 14, which is 194, and 360 minus 14, which is 346. So all we need to do now is just tidy it up for the marker. So the solution is in order 90 degrees, 194 degrees, 270 degrees, and 346 degrees. Okay, so the only difference with this question was that little 2 at the front, right, just means you double the expansion, but the process after that is exactly the same. For my final walkthrough, I'm going to do 3 cos 2x plus cos x plus 2 is equal to 0, and this time I'm going to do the range x between 0 and 180 degrees. So please note that I've changed the range to be between 0 and 180. So any answers that come out that's not in that range, I'm going to ignore. Normal process of expanding. So the expansion for cos 2x, remember we've got a choice of 3, but we're going to use the one that's got cos in it. So that's 2 cos squared x minus 1. And then we're just going to write down the rest as plus cos x plus 2 is equal to 0. We're going to remove the brackets there. 6 cos squared x minus 3 plus cos x plus 2 equals 0. And then we're going to tidy that up. 6 cos squared x plus cos x minus 1 is equal to 0. Okay, so we've done our expansion, we've done our tidying up. Next thing we need to do is factorise it into a pair of brackets. Now 6 cos squared x is 3 cos x times 2 cos x. 1 at the end means you have to do 1 times 1. For us to get a positive 1 in the middle, it has to be 3 times positive 1 and negative 1 times 2, so we get 3 take away 2 is 1. So there's our factors in the brackets. Last and final stage is solve these factors equal to 0. So 3 cos x minus 1 is 0, or 2 cos x plus 1 is 0. Looking at the first one, that's going to give us cos x equals, take the negative 1 over, take the 3 over, cos x equals a third. From our cast diagram, we're looking for cos being a positive number, so that's the A in the C box. From your calculator, when does cos equal 1/3? 71 degrees. The other one, 360 minus that, 289. The second factor equal to 0, that leads to cos x equals, take the positive 1 over, take the 2 over, cos x equals negative a half. Again, from your cast diagram, this time it's a cos question, but it's a negative one. So we're going to tick the places where the cos is negative, which is the S in the T quadrants. Okay, always find the related acute angle, the angle in the A box. So when does cos equal a half? From your calculator or from your knowledge of exact values, that's 60 degrees. Where have I got my ticks? X would be 180 take away 60 and 180 add 60. Okay, now ordinarily we would be finished there. However, remember a few minutes ago we spoke about the fact that we had changed the range to be between 0 and 180. So let's just check these answers. Well, 290, that's too big, so I'm taking that out. 240, that's too big, so I'm taking that out. So that then leaves me just with the answers of 71 and 120. So the solution to the question is 71 degrees, I could write a 1, 71 degrees and 120 degrees. Okay, so the same process as before, expand, tidy, factorise, solve, but this time keep a wee eye on the range. Make sure your answers actually satisfy the question that's being asked. Okay, so at this point here, it's got the wee pause symbol. So in a minute or two, when I tell you, you pause the video, there's 8 examples for you to work through. Once you've worked through those 8 examples, if you then start to play the video once again, I will give you the solutions to those questions. And as well as the solutions, I'll also provide worked solutions which will take you through stage by stage how to actually do it. Okay, so if you pause the video now, here are the solutions for the first 4 questions. Okay, so you can pause the video to get a note of those and check them against yours. Here are the solutions for the last 4 questions. Again, you can pause the video to check against yours. The worked solution for question 1. Pause the video, check your answer. The worked solution for question 2. Pause the video so you can check your answer. The worked solution for question 3. Pause the video so you can check your answer. The worked solution for question 4. You've got the idea now. The worked solution for question 5. The worked solution for question 6. The worked solution for question 7. Note the change in the range. And the worked solution for question 8, change in the range and radians. Okay, so just a plenary session just to remind you what we've been through there. Okay, so the method of solution is we do expanding the double angle. We then tidy up if it's needed. We will factorise common factors or trinomials, solve each of those factors equal to 0, and then convey your answer to the marker, putting them in order, looking at the range and making sure that your answer actually satisfies the range given in the question at the start. If we've managed to do all that, then that's absolutely brilliant, fantastic. I think we can now say that we can solve double angle equations. Okay, obviously it's a video, so you can go back at any time and watch any bits of it again. Last part from myself is if you would like a resource for more practice on these ones, especially the exam type questions, then if you make a note of that web address there, you will find literally hundreds, if not thousands, of different things. In particular, sections I like when we're doing past papers is looking at past papers by topic. So if you go to that section, click on the links for trig equations, you will find all the equations that have appeared recently in the exams, and you can see they're all worth about 4 or 5 marks. The solutions are there as well. Thanks for watching the video, and I hope to see you back for another one.